Hi, everyone. Welcome to the Technology Happy Hour. My name is Sarah Salkup. I'm a program coordinator here with Virginia Clean Cities. And today we will be hearing from Jessie Howell from the ElectraTherm team. Jessie joined ElectraTherm in 2020 as the North American sales manager. He spent 8 years in the combined heat and power industry, specializing in high efficiency, low emission reciprocating engine applications and waste heat recovery. Jessie believes in the value of waste heat to power and renewables for the future of sustainability and grid resiliency. Today, he will highlight how low temperature waste heat to power and gas to power can be an integral part of reducing our carbon footprint and utilizing an underutilized resource. But before we hand it over to Jessie, I have Alan, our executive director.
Hey, I'm Alan Harned here in Harrisonburg, Virginia. And I remember about 20 years ago, I was in the food service industry and my boss was wondering about waste heat energy capture back then. And so that was in a whole different energy era. Now we're doing a number of different vehicle and large scale community energy projects. And when I drive around Virginia, I do want to cap some of these heating flares, grab energy from those. And then also I see a phenomenal opportunity for turning waste heat into electricity in municipalities and projects throughout the nation. Some projects might have motors that are 100 years old that I'd love to capture the energy, turn that work back into other forms of work. So I'm just super excited about working with ElectraTherm and the possibilities for these technologies are great. I'm an early adopter technology type interested guy. So grateful to be a part of this.
Awesome. Thanks, Alan. And Jessie, I will turn it over to you.
Okay, I'm going to share my screen here and I'm going to shut off my camera for a bit to save some bandwidth. If that's okay.
That's great. And for anyone who's on, please feel free to unmute yourself and ask questions during the presentation or put them in the chat box. And then we'll also have a time for Q&A at the end as well.
Absolutely. I appreciate interjection with good questions during it and make it more of a conversation with a small group. Can you see the screen there, Sarah?
Yes, we can.
Excellent. Thank you very much. So as mentioned, today we're talking about turning waste heat into profitable power. The thing about waste heat is a lot of folks don't realize it's waste heat or that it's all around us. So it's about reducing our carbon footprint and creating some energy efficiency in a lot of different places that you may not have realized it's possible before. So a bit about ElectraTherm. We were established way back in 2005. If you're anything like me, you say, well, 2005, that was just a couple of years ago. And then you think, well, Jessie, you were in high school in 2005, so that was not a couple of years ago. We're a global leader in low temperature waste heat recovery. The key to that is that this low temperature waste heat is all around us. We just don't realize that it is. So what we're doing is boosting efficiency while reducing energy costs and emissions. There's no increase in emissions when converting this waste heat to power. We use what's called with an ORC system, and our systems generate up to 150 kilowatts of clean electricity, again, with no additional emissions or fuel consumption. The units are modular and scalable. So ElectraTherm, I think as we mentioned earlier, maybe that we are owned by BITZER Group. We were acquired in 2016. BITZER is a €1 billion a year company operating in 37 countries with over 3,400 employees. There's a big advantage with this because ElectraTherm is a small group and a flexible engineering team, but we're big enough being owned by BITZER that we can support all these remote projects. And we'll talk about some of the projects later that are operating in the US and some of the innovative ways that people are using this technology. So right now we've got over 100 applications globally. We're in 13 countries and approaching 2 million operating hours. And our Power Plus generator was successfully commercially released in 2011. I believe it was mentioned earlier in the introductions that, you know, this is not necessarily a new technology. It's an old concept, but the way it's being done now is very new. And the approach that we're taking is very new compared to how things were done in the past. So in a simple sense, it's basically if you have hot water, you have energy. So our units, the great thing about them is we convert heat to power no matter where that heat comes from. So I mentioned hot water a minute ago, but other heat sources can be converted to hot water. For instance, industrial waste heat. When you drive around, you see these stacks at manufacturing plants. Methane optimization, which is of course something that we all want to approach and look at with regards to Virginia. We hate to see flares. Wastewater treatment plants, landfills, anything that's flaring gas, this is a resource that could be utilized to make electricity. Boiler systems with biomass and biogas, they tend to go hand in hand with flare elimination. It's a resource that could be much better utilized to provide heat and power, which goes hand in hand with CHP and district heating. So our units not only can provide electricity, but also hot water for customers' usage. Then there's geothermal and co-produced fluids applications where we're literally getting heat out of the ground for power production. And of course, a byproduct of power generation itself gives off heat. So engines and turbines that are prime power producers give off enough heat that we can produce clean power from those as well. So today, what we'd really like to highlight is methane optimization. So right now, there's all this methane at landfills and wastewater treatment plants that this methane's not used effectively. So CH4 is one of the worst contaminants for the ozone layer. We know that. So why are we flaring it? Well, we're flaring it to get rid of the CH4 and break it down into carbon, which is bad for us. By converting those flares to boiler systems and creating hot water for our system, we can reduce those emissions and create clean electricity at the same time. Not to get too technical, but our systems do operate with an expander that allows us to turn down a considerable amount. What that means is we are capable of operating when others aren't. So extreme fluctuations in this landfill gas or wastewater treatment gas quality, or extreme fluctuations in the flow rate or quantity, our systems work very well with that, and we can eliminate flaring at these sites. That's what makes us a great fit for it. Also, sites where some of the methane is already being used, maybe in a boiler or an engine or turbine, we can use the heat that's a byproduct of that process as well. And I see a lot of interesting applications with these. For instance, there's a wastewater treatment plant that's looking at a unit right now that already has boilers for heating their digesters, but their boilers have additional capacity. So they have all of the infrastructure necessary to be converting that additional capacity and that additional gas to power right now. So we could 100% eliminate their flare just by adding this to their system that's already in place, and of course reducing those emissions substantially. Now, flare elimination, of course, that's a glaring reminder of how we could do better. I know it is something that Alan doesn't like to see, and I don't think anyone does. It's the waste of a resource. So I have a case study in here. It was actually a natural gas flare, which we, of course, are not going to run into in Virginia, but we do run into in different parts of the U.S. But it's a great example because you can see the amount of gas being flared here. But this is applicable to wastewater treatment plants and landfills instead. And the reason I like to highlight this is because it shows the emissions reductions. So even if you're not very familiar with these contaminants, we're reducing carbon monoxide by 98%, NOx by 48%, and VOCs, your volatile organic compounds, by 93%. That is huge reductions in emissions at a flare site. Now, the reason I give the disclaimer that's a natural gas flare is obviously your emissions are going to be a bit different at a biogas site or a landfill gas site. However, it's still going to be huge, significant reductions, and most importantly, a way to utilize this resource. So with these boiler systems, it's fairly simple. We're using that gas to make hot water in a boiler and then put that hot water into our system. So we've talked a lot about power already. Okay, we can provide up to 150 kilowatts of electricity out of it. But we can also provide heat outside the system for district heating or production of the gas or food production, even biomass drying. I've seen some instances where a customer burns wood waste for a district heating facility. So they have 10 buildings at this district heating application, and they have additional boiler capacity that they can operate this ORC system from. So in that sense, we create electricity from their highest temperature. And then our temperature outside the system, 185 degrees, is enough for their district heating system. So they actually have all of the equipment readily there to do this right now, and they could be producing emission-free power or no increase in emissions because they are burning wood waste. at their site. And it's a small footprint and a really easy integration since they already have that infrastructure. And you'd be surprised how many folks already do. So when we're comparing CHP processes with wastewater treatment plants and landfill gas, existing equipment is, an investment that's already made. Typically, you have digesters and you have boilers for keeping those digesters hot. The new equipment to go to an engine genset or very expensive. It's millions of dollars for biogas cleanup and storage. But if we're utilizing a boiler and a waste heat to power system, all that cost is avoided, and it's a much more simplified installation because the gas does not have to be as clean like it does for other instances. So we run across a lot of projects at landfills or water treatment plants where maybe they've looked at engines and it didn't make sense because of the cost for biogas cleanup, or maybe they unfortunately had a failed engine or turbine project because of gas fluctuations at certain times of the year production was down. That's an instance where the ORC systems with the expander we're using, we would be able to maintain operations through those areas of poor gas quality and quantity. For instance, we've looked at some landfill gas opportunities in Virginia where the gas quality was very low, maybe 34% CH4. So, your typical natural gas is 90%. With that being said, you couldn't burn that gas in an engine or turbine, but you could burn it in a boiler and make power from that resource currently. So the next area I really would like to talk about is industrial waste heat. The staggering number here is that over 90% of industrial waste heat is at temperatures too low for your traditional heat recovery. So kind of like it was mentioned earlier that it's not a new concept. Well, it's a new way of doing it because the old way required really high temperatures to make steam and power steam turbines. We're using a refrigerant fluid. So by superheating that, we can work with much lower temperatures and make use of all of this industrial waste heat, 90% of which is being wasted currently. Many of these industries operate 24/7 too, so they are actually wasting this resource 24/7. So if you look at like glass facilities and brick facilities, a lot of their kilns have to run 24/7 to maintain temperature. Otherwise, they destroy their own equipment by starts and stops. So that's a potential instance where we could be utilizing all of that heat that's already there. It's already a byproduct to reduce the carbon footprint of the site. Of
Mike,
course, at the same time, where yes,
Jesse, are you saying that you can use almost all of that 90% wasted heat? That much of it is a temperature that you guys can access?
absolutely. The vast majority of it, out of that 90%, I would say 99% of it is at a temperature that would be useful for ORC. The limiting factors with the stacks tend to be what's my cost to install, obviously, but if we're looking at reducing carbon footprint, obviously sometimes cost can not necessarily be a secondary factor, but a smaller factor than it is. But aside from that, a lot of these industrial sites already have some heat recovery. Take a brick manufacturer, for example. They have insane amounts of heat in these brick kilns, and they actually recover some of that already for the drying process further along. So they actually have a lot of the infrastructure there as well, and they have additional capacity. They could plug one of these in right now and increase their plant efficiency. And of course, by doing that, they're reducing their emissions. At some point, they're combusting something to give this heat, or some process is taking place. So in that sense, we're capturing that heat and reducing their total carbon footprint. A lot of these sites may have radiators. They might need to reject heats. Another good example I came across just today, there's a site that damages their equipment if they don't reduce. So they have a couple different heat recovery pieces of equipment in line. If they don't reduce the temperature from 1200 degrees Fahrenheit down to 500, they damage all of their equipment. So they actually recover this energy already, and they do nothing with it. They reject it in a radiator. So in that sense, this could be plugged right in, and it's easy installation. It's comparable to a radiator. Everybody, and that's one of the points I wanted to make when talking about these industrial waste heat sites. This is the kind of heat that's around us all, and we don't realize it because we're so used to walking past an air handler or a fan or a radiator, and you don't realize that's getting rid of a resource. So of course, with those projects with existing infrastructure, they have everything necessary already. It's a reduced CapEx and it simplifies installation even further. So with that being said, in those instances, it can be used for combined heat and power as well. So I think I mentioned earlier when talking about the biomass boilers, we could have up to 185°F water outside our system as well, or we can reject that water after the process, but still provide clean electricity. So it's a great way to offset cooling load at sites that already have radiators, or flat out just replace them. Some sites look at absorption chillers. Absorption chillers are also an old technology that's being done new ways, but it can be a very hard integration. So if you have heat available, it might make a lot more sense to look at converting that heat to power instead of chilled water. So geothermal sources, this is a area that was somewhat foreign to me until quite recently. I think it was mentioned earlier, I came over from the engine world. So geothermal is something that's very exciting. It's literally heat that's coming out of the ground. And we're seeing some sources that are in adequate temperature ranges for power production in the US, mostly out west, but temperatures between 190 degrees and 300 Fahrenheit that are viable for power production out of some of these wells. And there can be geothermal wells from hot springs, or there's sites where people look at a geothermal resource specifically for power production. There's even oil and gas sites, though, that look at utilizing the geothermal values of their fluids that they already have to produce clean energy from it. Power generation, I'm only mentioning this because I came from the power generation world. When you're combusting gaseous fuels to produce electricity already, you're giving off heat. So we're a great fit to plug into a lot of these resources that exist. And there are some installations in Virginia as well, where we can take the low temperature waste heat from the cooling system. So these big engines have radiators. We can use that in the system, or we can use high temperature heat from the exhaust gas. So there's a little diagram of it that you can kind of see here. Of the different ways of recovering heat from those sources. So it offsets cost. It's actually, there's some very interesting aspects to it. You can actually increase the horsepower of some of these engines by recovering the waste heat. So it's a very fast return on investment because these engines have to stay cool right now anyway. So although there's not a lot of sites in Virginia, there are instances that could be a very easy way to increase efficiency and reduce our carbon footprint. So just comparing some benefits, when we compare it to traditional CHP process, so CHP meaning combined heat and power, so recovering heat from a power generation source, we have the ability to directly offset the cost of electricity because we have no fuel cost. Our fuel is a byproduct of another process. We also have the advantage of being able to eliminate all flaring. So your traditional power generation sources are very limited at how much of a reduced load they can operate at, meaning they can't go down below half of what they're rated, whereas our system can go down to 10%. So with flare sites, when you have extreme swings in quality and quantity, it makes us a great fit. We're also a much lower capital expenditure, but also an easy installation. So I mentioned a lot of our instances, we can be looked at as a radiator alternative. That's exactly how easy it is to install this equipment. So you have a flanged hot water supply and return, hot water in, hot water out, and then a circuit breaker electrical connection. So I'll elaborate on that in a more simplified way in a bit, but it's a very easy installation when compared to other power generation sources. And of course, it's a very small footprint with that because we're not firing anything, we're just using wasted heat. So a lot of companies are approaching us right now, and it's a great thing about their ESG initiatives. So what 5 systems could do for people, and when I say 5 systems, I mean our small, like a radiator replacement systems. I'm not even talking about the larger systems, but it can be the equivalent to taking 500 cars off the road, or better yet, taking 500 cars off the road and powering a charging station for more electric cars. It can be the equivalent of the carbon sequestered by a 2,800 acre forest. And of course, reductions in carbon and powering. Another great example, enough emission-free power to power 280 homes year-round, from just 5 systems. And there's an abundance of sites that could handle 1 system, let alone 5. I've come across compression sites in the US where they had 36 different heat sources that could fit waste heat to power. And they're not heat sources that could be consolidated, they would be separate. So factors that we look for when examining sites are heat. Do we have enough heat at a high enough temperature? And you'd be surprised how often the answer is yes. I will run a heat balance scenario on any facility to determine whether they have enough heat. The second case is run hours. So this is where flares, like we talked about, whether it's landfill gas or water treatment plants, or the industrial waste heat are typically excellent fits because they have heat because we're combusting gas, and they actually have run hours. They have tons of uptime. So they're ideal fits for this equipment. And then, of course, the value of power comes into play, but not so much when we're really looking at ESG initiatives. So if they have electricity greater than 10 cents per kilowatt, they actually have a fast ROI. But a lot of times that's just a bonus. There's some instances where the value of offsetting that flare is much more important than the electrical, the rate benefit there. So right now we have three main products. Our largest goes up to 150 kilowatts, and our smallest unit is the active cooler, which acts as that radiator replacement. So it's designed to reject heat for sites. And we have a really cool application with the active cooler that's actually installed in Virginia, and I'll talk a little bit about later. So how it works, ORC is one of those things that sounds a lot more complicated than it actually is. The simplified way of looking at it is similar to a refrigeration compressor or even an air conditioning compressor. You put electricity into those compressors. They spin a small turbine powered by an electric motor or a screw expander compressor. So you put electricity in, they compress a refrigerant, and it cools your system or whatever you're doing. So we're doing the opposite. We're putting hot water in from the other end, and that is spinning the expander in this case, which then turns the electric motor and produces the electricity. So it's kind of like thinking about a refrigeration compressor or even an AC compressor in reverse. We're just putting hot water in and getting electricity out. So in the more technical sense, we're just boiling refrigerant in an evaporator under pressure that's going through the expander, which spins an electric generator and produces power. And then the vapor's cooled and condensed back into a liquid. We pump it to a higher pressure and return it to the system. So it's very important. It's a closed loop system. We utilize a low toxicity, non-flammable refrigerant that's housed in this. And it's a very safe and simple, not to mention robust system. So it's actually a bit interesting that the refrigerant goes through the generator itself and cools it as part of the process. So a lot of safety mechanisms built in with that. Now, current US installations, we've got some really cool installations in the US. So there's installation on Dutch Harbor that's actually some engines that are running out there, and they're making power from one of our Power Plus systems. The really cool thing about that, for one, Dutch Harbor is a really remote site, so it does show our capabilities of supporting those sites. But for two, they utilize a seawater heat exchanger. So with that being said, they don't have any parasitic cooling load from a radiator on our system. They're actually using ocean water to cool the refrigerant, obviously through a separate isolation heat exchanger, but it makes for a very efficient process. There's a biomass system in Quincy, California that is a very interesting site. I mean, actually very scenic there. You can see it in the picture to the top right. We've got a wastewater treatment plant in Staten Island. That's actually a picture of it there. It's a flare elimination project. Some biomass projects in California and Florida. The industrial waste heat project in Virginia, we'll talk about it a little bit more in a moment. That's a very good example of industrial waste heat that would be overlooked at a number of sites. And of course, we've got a unit on turbine heat in Maryland and an incinerator in Maryland, and even a solar loop. So a solar thermal heating loop down at the University of Louisiana. They have one of our older units that just approached its 35,000 hour maintenance interval. So significant run hours on that particular unit. But I know I've been talking a lot here, so I wanted to pause for a second and see if there's any questions before I talk about the installations. We're nearing the end of the presentation here, but I wanted to check before and see if there's anything on anyone's mind.
I actually had a question that was submitted to us prior to the event from someone who was not able to actually attend today, but was asking, is this technology beneficial to use residentially? From what I'm seeing, it looks largely industrial, but if it is, how would that be used, or is that a plan for the future?
So on a single family scale, you run into an economic scale with waste heat to power because of the heat exchangers required to convert that heat to electricity. On a multifamily residential scale or a community scale, it can be a very good fit. Particularly out west, I've run across some opportunities where they're building communities. They're building communities with geothermal heat sources and powering the entire communities off of geothermal heat. So in a sense, that's not waste heat, but it is heat that is available to power. But I've seen the same done with some district heating on biomass. There was actually a site in Tennessee that looked at doing that in the past. And there's a couple sites in the Northeast where they actually utilize biomass boilers for a district heating source. And then they power plus systems from hot water as well. So on a single family residential, I would say the scale isn't there. For multifamily and community type installations, it can absolutely be a great fit.
Thank you.
Yep.
I had a question, Jessie. This is Amy with Virginia Clean Cities.
Yes.
I was wondering, what are some of the applications used in other countries with this technology? And is this something that could conceivably help developing countries, for example, obtain clean energy sources? Although I'm not sure because they would likely not have the infrastructure, but perhaps if they have things like geothermal, that could be something that they could tap into.
Well, so absolutely. And it comes down to the individual country as far as the product mix, even aside from developing countries. So we look at developing countries, there might be a waste issue at some. So we've had some requests in Africa before where they have some sort of bio waste or biogas that's available. And that would be along the same lines as these flare elimination things, where we could be an integral part of a microgrid by combusting a waste heat source. As you mentioned, geothermal resources could be very good in certain areas. Even some of the remote areas in Mexico that have some hot springs could be a great fit for geothermal resources. And other South American countries and more developing countries, I should say. Maybe that's not a good example, but it comes down to that. So with regards to installations overseas, for instance, you see a lot of different stuff in different regions. So the UK, for instance, has a lot of biomass sites. They combust a lot of wood waste for their district heating. So we have a number of biomass installations there. Japan has a number of geothermal resources. So Japan has a lot of several installations based on that, some really big ones as well. The US, we see a little bit of everything. And the same goes for Canada. So lots of different options and opportunities.
This is Natalie. If I can jump in for just 1 second, I would also add there are some instances of like island nations, for instance, that have very not green sources of energy currently. They're utilizing diesel generators in a lot of instances. We can use ORC in combination with that to at least green some of those existing processes. It's not an elimination, but it is an extender, and it does green at least some manner of their electric network. So I just wanted to add that as well.
And absolutely, I appreciate that, Natalie. That's a great example, because even Jamaica, for instance, has diesel engines running 24/7 at sites. And cleaning those up just 10% does a lot for the environment. 10% might not sound like much, but that's huge when you're talking terms of diesel reduction. But you know, also a lot of those engines in the future could be modified to run on hydrogen, so they can clean up even more, and we could already be recovering that waste heat and converting it to power. It's also a great example because there's Pacific islands that are that have a waste problem, as I mentioned earlier. So they might have landfills, and some of these places actually store waste from other nations. It's not an island, but in my previous life, I did a project in Mexico City that was actually paid for by Fuji out of Japan because they had waste in the landfill. So it was a Mexico City landfill that has a CHP that was funded by a Japanese company. So in a lot of those developing areas, you might find it interesting to see who would invest in cleaning a lot of that up. And I've looked at that before with biodigesters in different countries as well. And not to mention, so the example I gave in Jamaica was diesel, but there's propane units running elsewhere. So we mentioned, you know, VOC reductions and things of that nature. That's a huge instance where we could be reducing our carbon footprint, or the carbon footprint of a client, I should say. Any more questions before I talk a little bit about these installations? There's not a lot to cover here, but it's very interesting stuff. All right, so moving on to this, this installation in Virginia is really interesting to me. So it's a pharmaceutical facility, and the heat source is a water-cooled air compressor. So they had a pneumatic system, and apparently for this sanitary process they have, it required an oil-free air compressor, which happened to be water-cooled. So that unit always had a little radiator that was rejecting heat 24/7. And with that low temperature heat that would, you know, you would typically walk past these air handlers and fans, we're making 45 kilowatts. So we're probably saving them $30,000 to $40,000 a year, not to mention we're reducing that overall carbon footprint. So they were using, they were wasting electricity in this radiator, you know, year round, and now they're not. Flare elimination in New York, again, we're making 44 to 48 kilowatts, but the big thing is that flare is not going to have an orange flame over it anymore. It might be there for backup if there's boiler maintenance or something that's there, but it won't be operating at that point, and could actually be reduced in size. The pandemic did slow down commissioning on that unit, but it is on site. It is able to run, and it's just going through the final connection processes that were slowed down by the pandemic. To summarize benefits, we are emission-free power, fuel-free, as long as our fuel is a byproduct of another system, and a robust, reliable system. So it's a 20-year design life, approaching 2 million operating hours, and we also have great global support. A very easy installation. Again, it's comparable to installing these radiators that people just walk past everywhere. A lot easier than installing a flare or an engine or a turbine. And they're easy to operate and maintain. These units are designed for when you have heat available, they're up and running, and when you don't, they shut down. But they can start back up again without any interference. Unattended operations, so to speak, with remote monitoring. And right now they're qualifying for some incredible investment tax credits. So this would only be applicable to tax-paying entities, of course, but your industrial manufacturers, your places that already have a lot of this heat, there's a 26% federal investment tax credit currently. And 26% typically takes at least a year off of a return on investment for these. And the reason for it is to make an effort to reducing our carbon footprint and utilize a resource that 90% of is currently wasted. There's also other states that have very nice incentives as well from their utilities. So it's important to keep up with some of the incentive websites, DSIRE, and those to know what might be happening in your states as well. So that was it for the presentation. I'm, of course, available for any other questions we have now.
Thank you so much, Jessie. That was a great presentation. And if anyone has any questions, like Jessie said, please feel free to unmute and speak away.
Alan, I think you mentioned earlier about, it was either you or one of our other attendees mentioned it's an old concept and some of these older sites that were designed a long time ago. We came across a college campus today that the central boiler plant was built in the 1930s and still had 2 of the original turbines.
Yeah, we have so many different systems that were built before this technology was feasible, or maybe when steam of water was the closest thing. And so I loved your slide about the amount of opportunity that's here. We work with so many cities that have just base their systems on this aging technology. And I see so many wonderful opportunities, Jessie. And we just need to communicate properly to the operators of these heavier pieces of equipment. We need to identify the waste and to motivate.
That's exactly the key, is identification, because you can't do anything about it if you don't realize it's a problem or a resource. And that's what we run across a lot. Like these city district heating networks we talk about, where they're on steam systems. Some of these have blow-by systems that are so big, just the blow-by system could produce clean power from it. And they already have this resource, you know, it's there, it's just underutilized. I can't even read my own notes here. I had some other ones about some of these older districts and things, but unfortunately I missed it. I'm getting much older. That 2005 has caught up with me now.
Everyone, you can just, Jesse's sandbagging. He can't remember anything because he hasn't slept since he had twins born this year. So Jesse's a new father.
That's the reason for the headset. So you can't hear them.
Congratulations.
Thank you. Well, are there any other questions? It's hard to believe that we've spent 45 minutes already. Time flies when I'm rambling on.
Awesome. Well, if there aren't any other questions, I'll just take a second to plug our next Tech Happy Hour event. These events are monthly. Next month in October, we will have BEIC on to talk about their work with energy solutions, transportation electrification, and some of the work that they're doing with electric school buses. So if anyone is interested, the link is in the chat to register, or you can peruse our website at vacleancities.org/events. There are also a bunch of really great in-person and virtual events coming up in September and October as we approach National Drive Electric Week. And there's just a bunch of really good clean energy events coming up. So I recommend anyone who's interested to head on over and peruse that site.
Thank you very much for the time this afternoon.
Thank you, everyone. Hope you have a great rest of your
Yes.
day. And thank you, Jessie.